Thank you, Tom. So welcome to this statistics taster lecture. First, a bit about me. I'm Lisa Mott. I'm teaching associate in the School of Mathematical Sciences at the University of Nottingham. The main teaching I do is on the degree apprenticeship in data science. My main interests are mathematical education and in particular digital learning. And an interesting fact about me is I was the first in my family to go to university. I did my PhD in statistics at Nottingham, modelling white matter in the brain. So the aims and objectives of today's taster session. So we're going to understand the importance of visualising data. We're going to consider extrapolation and its limitations. And we're going to introduce the normal distribution and the combination of two normal distributions. So our first motivating example, we're going to look at this data by Francis Anscombe in 1973. So W1 is essentially 11 numbers, and the mean of these 11 numbers is 9 and the variance is 11. So just as a reminder, if we have some data, so n numbers, x1 to xn, then the sample mean means we add them numbers up and divide by how many there are, which we can write in the following notation instead. And the sample variance, we have each number, subtract that sample mean and square it, add that up for each of the numbers in the data set and divide by n subtract 1. In our case, n is 11 because there's 11 numbers in W1, so it would be divided by 10. And what we actually see is we've got W1, W2, W3 and W4, which each contain 11 numbers, and the sample mean of each of these sets is 9 and the variance is 11. And similarly for Z1, Z2, Z3 and Z4, which are also 4 sets of 11 numbers, the sample mean is 7.5 and the sample variance is 4.13 or 4.12, depending which one it is. Now, we might think, well, what's the correlation between, say, W1 and Z1? Is there a linear relationship between them? And what is the correlation between them numbers? Well, we can use Pearson's correlation coefficient, which you may have seen before as this. And interestingly enough, the correlation between W1 and Z1 is 0.82, the same for the other 4, so W2 and Z2, W3 and Z3, and W4 and Z4. So it seems like there's a positive correlation between the two sets of numbers in each case. So the first thing I would like you to do, the quiz is going to get posted into the chat, but also you'll see a barcode come up in a second, which you can use to go on to the to answer the question instead. Do you think these data must be the same? So is the set of 11 numbers in W1 the same as the set of 11 numbers in W2, W3 and W4? And similarly for Z1, Z2, Z3 and Z4, must these be the same 11 numbers in each of them? And what would you suggest we might do to check this? So if you could please answer the questions. I know there's a 20 to 30 second lag, so I'll try and give you 2 minutes from this time now to do this, which will be about 1.5 minutes to 1 minute 40 seconds when you hear this. Okay, so we've got quite a few responses. It seems the majority of people are saying actually no. There's some not sure and some impossible to tell, but nobody's actually wrote yes, and we've now got more no's. So we will have a look at this. So we've had quite a few responses. People have said we could calculate the standard deviation. This would just be the square root of the variance, so this would be the same. We've actually got a few good suggestions of actually plotting the data. Let's look at a scatter plot and see what we can tell from this. Now, before we actually do the scatter plot, we're going to look at something else. This is the actual data. So I've renamed them X and Y's now. They were W and Z before. I didn't want you to get confused with the sample mean formulas from before. So the first data set, the second, the third and the fourth, we can actually see that this fourth one, X4, it looks different to the X1, X2, X3. So they're clearly not the same. And also the Y values are different in all of them. what we're going to look is if we did a scatter plot of this data and we actually wanted to have a line that represents that data. So we've got X on the X-axis and the Y values on the Y-axis, and say this is X1 versus Y1. How do we find this line that best represents this data? Well, one method that we can use is between the Y coordinate of the data point and the Y coordinate of the line. Calculate the difference in that. That's the error. Now we've got 6 points here, so we'd have 6 errors. And because some of them are negative and some of them are positive, we're going to square the values. This is least squares regression. So we want to find the line that minimizes, makes as small as possible, the errors squared, all added up of this. So we essentially want to find a line that is as close to them points as possibly can be, such that the errors squared are to a minimum when we draw that line. And there's other methods you can do to find a line that represents this data, but least squares regression is among the most popular. And when we use this method, we find that for Y1, the linear regression line is Y1 is equal to 3 plus 0.5 X1 for that Anscombe data. It's the same for Y2, Y3 and Y4. So we clearly know that the data is not the same. We've seen the data, but we've got the sample mean is the same in all of them. The sample variances are the same. The correlation between the X's and Y's are the same, and even the linear regression lines are the same. So we're going to use your suggestion, which is to actually do a scatter plot of the X1s versus the Y1s, etc., to see what we can tell from that. So when we plot X1 versus Y1 and draw the linear regression line on there, we can see it's quite a good fit. It seems to fit the data quite well. X2, Y2, that is not a linear shape. We can see that probably a quadratic might be better to represent that, but the linear regression line that we draw on is the one that would minimize the error squared, but clearly the data is not linear. For X3 and Y3, we've got this outlier here, which pulls the line up, and we'd have to check whether that outlier should be there or not. It might just be a strange case. It might have been a mistake that's been made if we had something like this. And for X4 and Y4, we've got this strange point here, which then pulls the line up this way. So we can clearly see that the moral of this first part is that we should always plot the data first, and even though we can use any statistical method on some data, first make sure all the assumptions are met to use the method. We can see that, for example, for the linear regression, we could only use that on X1, Y1 because that was the only one that was actually linear. So the second part of today's lecture, we're going to look at the 1 mile run world record. So since 1913, they've been collecting the world records for the men's 1 mile run. And we're going to look at these up until 1954. So the world record for completing 1 mile in running for men, in 1913 when they started, it was just below 255 seconds. And it's gone up until 1954, it was just below 240 seconds. And we can also view it like this so we can see when the world record wasn't changing. But interestingly enough, it seems that it actually follows pretty well a linear relationship. And if we use linear regression, the line we would get is that the world record time, Y, is 927.9915, subtract 0.3521 multiplied by the year. So what I'd like you to do, please, if you can click on the second link in the chat, can we use this line, do you think, to make predictions about future years? The barcode's also there, so this line that we've got, do you think we could use that to make prediction about years after 1954 for the world record time for the 1 mile run? Okay, we've started to get quite a few responses in now. it actually seems that the majority of people think, no, we can't use it to predict the future years. There's quite a few people who've also said yes, but most people have said no. And there's some people who've also said not sure. The reason for your answer, one good point is eventually it would hit 0, which is of course impossible. There's some people mentioning about there'll be limits eventually with human biology about how fast people can actually run the 1 mile. Yeah, so people are saying that eventually there is going to be a limit where we can't actually get any quicker than what's already there. So let's actually have a look. So if we did use the line to do the prediction of what it would be in the year 2000, then replacing x with 2000 in that formula, we would actually get that by the year 2000, the world record would be 224 seconds with that line. That is what happens up until the year 2000, which surprisingly does look pretty linear. If we did that line on, we can actually see that after 1954, they were actually all of the times were quicker than what the line predicted. If we did the times from 1954 to the year 2000, then this would be the line that would represent, best fit the data for the times from 1954 to the year 2000. So it's actually quite remarkable that this pattern did seem to go on for this long. And this would be the linear regression line that would just be the best fit from 1954 to the year 2000. Whereas prior to 1954, this would have been the linear regression line. So will this trend continue? Well, we'll actually have a look. So we'll skip question 3. I'm just a bit conscious of time. But actually, after the year 2000 to the up until a week ago when I last looked, there'd been no new world record since the year 2000. So maybe, as people were saying, maybe the limits of humans has been reached, maybe not, maybe it will actually go down again. But if that original line had continued the trend, then when X is 2020, the world record in 2020 using that line would have been 216.75 seconds. So for this second part, unexpected things may happen. As we saw, we didn't expect the trend would continue after 1954, but it did until the year 2000. But there is probably a limit at some point, so be careful about extrapolating data, looking beyond the data that you have. So we're going to look at the normal distribution now. So there's many applications of the normal distribution in all areas of science. And the normal distribution has a bell curve shape. We can see it's got this bell curve shape with a maximum here. And as we move away from this point here, it's actually less and less likely that these values will be reached, but they're still possible. Now, the normal distribution is described by 2 parameters, the population mean, which will be this value here, and the population standard deviation. And the standard deviation lets us know how spread the data is. So, for example, these are 2 normal distributions, these curves. We can see the population mean is at the same point. However, the blue curve has a larger standard deviation because it's more spread, the values that they can have. So, interestingly enough, with a normal distribution, if you were to look at the values that were a maximum of 1 away from the population mean, could be the population mean plus 1 standard deviation, or the population mean subtract 1 standard deviation, then 68.2% of the values should lie within 1 standard deviation of the population mean. And we can see that typically most values from a normal distribution lie within 3 standard deviations within the population mean, within 3 standard distributions away from the population mean. So we're going to look at some height questions because the normal distribution can be used to model height. So in England, the average height of men is 175.3 centimetres and a standard deviation of 7.4 centimetres. We have some values for the height of women as well, but we're just going to focus first on a problem with the men's heights. So this would be a histogram of 10,000 heights for men in England using that normal distribution. And we can see that we've got this bell curved shape that represents this distribution. So I've got a few questions for you, which is approximately how many of the 10,000 men will be between 175.3 centimetres and 182.7 centimetres if we measured 10,000 men in England. Approximately how many of them would be less than 160.5 centimetres? Approximately how many of the men would be between 160.5 centimetres and 190.1 centimetres? There's an extension question. If you could have question 4 in the quiz, please. And there's also the possibility of scanning that barcode to go on to the quiz. There's 2 diagrams there that should help you, and there's also a reminder at the top of what the population mean is and the population standard deviation to help you with that. If you'd like to now, please submit your answers. I'll give 30 more seconds before I move on. One thing that it is useful to actually look at is the diagram and what percentage is actually within these. So what we're going to do now is actually look through the solutions and see how we could do this both in a theoretical way and using approximations. So actually for question 1, the majority of people did get the correct answer of 3,410. So approximately how many of, well, if we look at the diagram, we know that the mean is actually 175.3, so this will be where this peak is here, and the standard deviation is 7.4, so 7.4 added on to 175.3 will be 182.7, so we would expect that these values would lie in this pink region, because it's 1 standard deviation away from the mean, which is 34.1% of 10,000, which is 3,410. We're also going to look at how you could approximate this answer using R, which is a statistical computing language. So what we could do is we could generate 10,000 random variables from a normal distribution with a mean of 175.3 and a standard deviation of 7.4. We could set the counter to be 0, so that we're saying, first of all, we've got no heights that are between the range that we want. And then for the 10,000 values, if the heights between 175.3 and 182.7 of the 10,000 values we've got from this normal distribution, then add 1 to the counter. So it's essentially counting how many of these 10,000 heights that we've randomly generated, how many of them are actually between these 2 heights. And using R, this is actually 3,365, which isn't too far from the theoretical answer of 3,410. For the second one, which was how many of the 10,000 guesses are less than 160.5. Actually, again, you've all done pretty well on this question. So what we can see is this will be this blue and this white bit on the curve, because 2 standard deviations away from the population mean would be 160.5, so anything less than that will be in this blue and white region, which if half the curve is the yellow, orange, blue and white, then to find the blue and the white, it's 50, subtract 34.1, subtract 13.6 is 2.3%, which would be 230 would be 2.3% of 10,000. A lot of people actually put 210 because they didn't notice that after this 2.1 we've actually got this white bit here, which is 0.2%. And using R, we could do a similar thing, set the counter to 0. For the 10,000 values, count how many heights are less than 160.5, which we found the approximate value using R is 225 compared to the theoretical value of 230. Similarly, for question 3, we see that it's the orange, yellow, pink and green bit because it's the ones that are within 2 standard deviations away from the population mean, which would be 95.4% is 9,540 of the values. And in R, we can do a similar thing to actually find that in R, using some simulated data, it would be 9,560, which is pretty close to the theoretical value of 9,540. And again, you did quite well on question 3 in general. For the extension questions, a lot of people have mentioned integration. Yes, we can use integration, and if we can't do that theoretically, we can do that numerically. You might have met the trapezium rule or Simpson's rule in your A-level studies, and numerical approximations is another active area of maths. So we're going to look at the final part of today's talk, which is combining normal distributions. So we've looked at what a normal distribution is, and we're now going to look at actually combining normal distributions. So as mentioned before, in England, we've got the average height of men. For women, it's similarly 161.9 centimetres is the average height, and the standard deviation is 6.9 centimetres. So we've got for 10,000 women and 10,000 men from a normal distribution, these would be the histograms with the normal distribution curve plotted on them. So say that we have the heights of 10,000 men and 10,000 women. We know both come from a normal distribution. If we had the 20,000 heights, which is the heights of the 10,000 men and the 10,000 women, and we plotted these 20,000 heights onto a histogram, do you think that the histogram, the overall distribution, will it be unimodal, which means will it be similar to the ones for the separate men and women? Will it just have one peak, like these histograms? Will it be bimodal? So will it have 2 peaks when we plot the histogram? Or will it be neither of these? So could you please click on for question 5, the quiz, or scan on there, please? I'll give 1.5 minutes from when I've said this. So interestingly enough, about half of people who've responded have said bimodal, and then about a quarter of people have said unimodal, and a quarter of people have said neither unimodal or bimodal. Now, if we actually plotted the combined of these, it would actually be unimodal, interestingly enough. So people tend to think it would be bimodal, but when we combine 2 normal distributions, in this case, it is unimodal. And when we do this on R, simulate these 20,000 values and do the histogram, we can find that the mean height is 168.6 centimetres, and a standard deviation is actually greater than for the men and women separately. It's actually 9.8 centimetres. So we're going to look at one final example today, which is about some conscripts in France. So in this book that's mentioned here, it looks at the heights of conscripts in France from the 1850s. So there's 2 groups of men who are in the conscripts. There's the Celts and there's the Burgundians. So what I would like you to do, please, either on the quiz that comes up or this barcode, this is the height of the 8,000 conscripts in inches. Can I get you to write what this graph appears to show? Can you trust this, what you've said? And what might be a different reason for the 2 modes that there appears to be? So we've actually had some responses. We've had some saying about that it looks like there's 2 different categories, or the distribution's bimodal. People have put that they can't trust the assumption they've made, and different reasons for the two modes. There's been suggestions about too small of a sample size. There might be data missing. They might have lost some data between here. There's also, yes, somebody's put the mean is between 61 and 62 with a bimodal distribution. So when we looked at the actual data for the men and the women heights, and it turned out it was unimodal when we combined them, it seems a bit strange here that it's actually bimodal. So we're going to look what actually happened with this data. So originally, when they took the heights of the conscripts, they rounded the height to the nearest centimetre. So for example, if they were 160.6 centimetres, they would round the height to 161. Then the new heights were converted to inches, and then they were rounded to the nearest inch, the new heights that they had. So we're going to simulate this on R. So say that there was some, the heights had a mean of 156 with a standard deviation of 4, and we're going to have 8,000 heights from this normal distribution. Then what we're going to do is we're going to use this floor function so that, for example, if somebody's 160.1 centimetres, we're going to record the height as 160.5. And then for each of the values, we're going to divide them by 2.54 to convert them to inches. And we're going to see what happens when we plot these values. So if we plot the 8,000 transformed values that we had in inches, then we can see it's clearly bimodal. If we actually do a histogram of the original heights, then we can see that it's unimodal. So this is the same data, it's just been transformed in a weird way, and one of them's unimodal and the other one's bimodal. And why does this happen? Well, a height of between 152 and 153 centimetres, if we say that that's 152.5, then changing that to inches gets us 60.04, for example. And we can see that the ones in yellow, so the heights between 152 to 155 centimetres, would be classed as 60 to 61 inches, whereas the heights between 155 to 157 centimetres would be classed as 61 to 62 inches using this method. And the ones from 157 to 160 centimetres would be classed as 62 to 63 inches. So the problem is that this category of 61 to 62 inches only has a range of 2 centimetres, whereas the others have a range of 3 centimetres. And this is why we get this dip in the histogram. So the moral of this point is don't trust some data or graphs unless you know how it's been collected and measured. So as a conclusion, we've only just touched on a few problems in statistics. Don't trust all results that you see reported as fact. Any questions are welcome, but before we go to the question and answer session, just going to mention that in the bachelor's and MMaths degrees that Nottingham do, there's a lot of choice of statistics modules. In particular, in the year 1, everybody does some statistics. In year 2, there's a statistical models and methods module, which goes into more detail of some interest in statistics. And as you can see in year 3 and year 4, this is just a few of the modules that we offer in year 3 and year 4, which cover a wide range of different interests in statistics that you may want to focus on later on. There's also the barcode here on the website for a study with us page, which looks at the different maths courses that are offered at Nottingham. And some of the open day maths talks that we've had previously, the videos can be found on this link here. I believe these links are also in the chat. We've also got some information here about careers that maths graduates go to after studying a degree at Nottingham. And there's also a newsletter that you can sign up to, a recent newsletter, where you can receive news about maths at Nottingham, interesting facts, puzzles, and links to some useful resources. And finally, some previous taster sessions and popular maths talks that we've had previously, including some in calculus, some in using maths in the fight against COVID-19, and some other interesting talks can be found on this link here or using this barcode. I'm now going to hand over to today's host, Tom, to carry on.